All right, we are starting chapter 14, which is going to change pace for the past handful of chapters, really 10 through 13. We've been talking about solids, liquids, gases, and solutions. Now we're going to talk about kinetics, which is a whole different ball of wax when we start talking about chemical reactions. Excuse me. So that's really going to change things up here. So we're completely changing kind of what we're doing. What is kinetics? Kinetics is the rate at which a chemical process occurs. So what we're going to be studying here is the speed at which a reaction occurs and the concentrations that occur during, or the concentration of those reactions. So kinetics is the rate at which chemical processes occur. And you guys know this, some reactions occur instantaneously, some take a little longer to undergo or to occur. So why is that? And kinetics is going to kind of help us reveal that. So we're going to try and do, what we're going to try and do is we're going to try and take some math and some calculus and apply it to chemical equations. So that's kind of the process of kinetics. So when we talk about factors that affect chemical reactions, there's a couple. First off, the physical state of the reactants. In order to react, and this makes total sense, in order to react, molecules must come in contact with one another. Well, what type of mixtures come into more contact with one another? Homogeneous. Think about it. Because the molecules are completely dissolved, they're going to be completely in more contact than a heterogeneous mixture, and in a homogeneous mixture they're going to react faster because they are dissolved, they're in more contact. All right, so that is homogeneous mixtures are going to have more reactions. Other things that affect the concentration or the reaction rate is concentration. The higher the concentration, the likelihood the molecules will collide. So if we have a higher concentration, the rate is going to be affected. So two things. Two things so far that are really the type of solution, homogeneous, concentration. Next we have temperature, and we've talked about this. At higher temperatures, you have more kinetic energy, therefore the molecules are moving faster, therefore they're going to collide more often. If they collide more often, they have more of a chance of reacting, so your reaction rate is going to be changed by temperature, so warmer temperatures. Lastly, the presence of a catalyst. What is a catalyst? A catalyst is something that speeds up the reaction by changing the mechanism of the reaction. It doesn't change the reaction, it just changes the rate or the mechanism of the reaction. Catalysts are not consumed during a chemical reaction, they just speed up a reaction. So, four things that can affect reaction rates. We have the physical state of the reactants. Remember, homogeneous solutions are going to react a little better than heterogeneous. We have concentration of the reactants. Higher concentration means those molecules are going to collide together more. Temperature. At higher temperatures, you're going to get more collisions, which is going to affect your reaction rate. And then you have the presence of a catalyst, and a catalyst is something that speeds up the mechanism of a reaction, but is not actually consumed during the reaction. So if we look at reaction rates here on the picture here, we have 0 seconds, 20 seconds, 40 seconds, and you can kind of see the reaction rates as we go. So how do we figure out a reaction rate? Well, all we're doing is we're monitoring the concentration of a reaction over a course of time. So you can see here, this is a very simple picture up here. At 0 seconds, we have 1 mole of A, 0 moles of B. At 20 seconds, 0.54 moles of A, 0.46 moles of B. And at 40 seconds, 0.3 moles of A and 0.7 moles of B. And when we monitor concentration, what we're going to do, or excuse me, when we monitor reaction rates, what we're going to do is we're going to measure the concentration of our reactants and products over the course of time. So, if we look at a reaction like this, in this reaction, the concentration of butyl chloride, which is C4H9Cl, was measured at various times. So we have butyl chloride reacting with water. All right, and we get our two products. What we did is we measured the concentration of butyl chloride over time. Now, what's happening to the concentration of butyl chloride over time? It's decreasing. Why is it decreasing? Most likely because it's reacting to form our products. Now, if we take this reaction and we figure out our rate, all right, our rate of reaction, now we've measured our concentration at various points in time. So now we have figured out our rate. Now, how do we figure out our reaction rate? Well, the reaction rate is a very simple equation. All right. Reaction rate, I'll write it on the bottom here, is equal to change in molarity divided by change in time. So for each one of these, for example, this one, we took the change in molarity divided by 50, and we got 1.9 times 10 to the negative fourth. Down here, we took the change in molarity between these two and divided by 100 seconds, and we got 0.8 times 10 to the negative fourth. So all we did to figure out the reaction, the initial reaction rate was figure out the concentration over time. Now this is a very easy introduction to how we figure out reaction rates. So note that it's the average rate. We're figuring out the average rate. Now what we can do is we can graph this information and we can figure out the rate graphically as well. So when we go ahead and do that, it's going to look like this. All we did is we graphed our concentration on the y-axis over time on the x-axis. And you can see here it slows down. Now, what's important to note is this. The slope of the line, all right, the slope of a line tangent to a point is the instantaneous rate at that time. So anytime you want to figure out the slope, you're going to pick a point tangent to that point. So you can see here at the top of the graph, the slope is pretty good. As the reaction starts to slow down, the slope slightly narrows. Now, what's important? The reaction is going to naturally slow down over time. Therefore, if you want to figure out the instantaneous rate of the reaction, it's best to do it at the beginning. So it's best to do it at the beginning, or the tan box here, or the tan slope rather than the blue slope. So the instantaneous rate, because this is right away at the beginning of the reaction. All right? So the reaction rate tends to be best at the beginning. So you measure at the beginning, not at the end, because as you can see here, it starts to slow down. So something to measure with reaction rates. Now, reaction rates and stoichiometry. You can note here that everything was 1 to 1 to 1 to 1. This equation was balanced with a 1 to 1 to 1 ratio. So when we do that, our rate is equal to, since it's a 1 to 1 ratio, our change in molarity of butyl chloride over time is equal to our change in rate of butyl alcohol over time. They are equal to one another because it's a 1 to 1 relationship. Now, what happens is if our ratio is not 1 to 1? All right. What happens if our ratio is not 1 to 1? What we're going to do now is, you can see here we have a 2 as our coefficient in front of hydroiodic acid, all right, breaking apart into hydrogen and iodine. But it's a 2-1-1 ratio. What's going to happen? Well, in that case, you're going to take 1 over the coefficient is equal to the concentration over time. So what do I mean here? If you see this, hydrogen, HI has a 2 out in front here. So we're going to take 1 over the coefficient, so we have 1/2 times our concentration over time is equal to I2. Well, there's no number out in front of I2, so this is really 1 over 1, or just the concentration over time. Now, if we take this and break it down a little further, to generalize, if we have little a plus a, all the little letters here are our coefficients. Our big letters are our concentrations or our solutions or our compounds that are reacting. So little letters are our coefficients, our big letters are our compounds that are reacting. So our rate is always equal to negative 1 over little a, remember that's coefficient, times the concentration of A divided by time, which is equal to negative 1 over B. Negative 1 over B times the concentration of B over time. Now our reactants are going to be negative, our products are going to be positive. So 1 over our coefficient is always going to have that rate. So 1 over A, negative 1 over A is equal to negative 1 over B, which is equal to 1 over C, which is equal to 1 over D. And then we're going to take the concentration divided by the change in time for all of those. So when we're looking at concentration and rate, they are going to give us information, all right, to kind of help us out. When we're looking at concentration and rate, those are the two pieces of information we're going to need to kind of figure out a reaction mechanism. So we look at one last reaction here for section 14.1. We have ammonia reacting with nitrite to form nitrogen gas and 2 molecules of water. So you can see here, when ammonia doubles, the initial rate doubles. So you can see here, 1 to 2, our rate doubles. 2 to 4, our rate doubles. 2 to 4, our rate doubles. All right. When NH4 doubles, the rate doubles. That's something to kind of keep in mind here. Likewise, when we compare the same equation in experiments 5 and 6, we see that when NO2 doubles, the reaction initial rate also doubles. So you can see here, we go from 0.20 to 0.40, our reaction rate doubles. 0.40 to 0.80, our reaction rate doubles. What the heck is this telling us? Well, this means that the rate of NH4 is equivalent to the rate of NO2. Therefore, if we are going to write a reaction equation for this reaction, it's going to be written as K is equal to the concentration of NH4 times the concentration of NO2. And K being the kind of rate law constant, all right, which will always be given to you. So K is the rate law constant, NH4 is the concentration of NH4, NO2 is the concentration of NO2. Now, what's cool about this is this equation is called a rate law, and K is the rate constant. So here is our rate equation. How fast is this going? So if we look at the rate laws, they're going to show us a rate law or equation is going to kind of factor in our concentration of our reactions with our rate. And it's always going to ask you what's the order of the reaction. Is it a first order reaction, second order reaction, third order reaction, fourth order reaction? The exponents tell us the order of the reaction. So since our rate law is K to the NH4 to the first times NO2 to the first, it's a first order reaction in NH4 because it's an imaginary 1 here, and it's a second order reaction in NO2. So just kind of keep that in mind. So it's a first order reaction in NH4, it's a first order reaction in NO2. Now they may ask us to solve for what is the overall order for the reaction. When they ask you to do that, you're going to add the exponents together. You ignore the rate constant because that's K, and you're just going to look at NH4 to the first, 1, plus NO2 to the first, 1. 1 plus 1 is 2. Therefore, this is a second order reaction. So this is just a brief introduction to rate laws. We're going to spend additional time understanding rate laws, dissecting rate laws, and doing some math with rate laws. But this should conclude section 14.1.